The third and the biggest of the three theorems, the most important, the one that is definitely guaranteed to be on the exam, is the mean value theorem. The mean value theorem, in essence, is a derivative finder. Okay, the mean value theorem has two parts to its condition. Once again, the function has to be continuous on the closed interval from a to b. But just as importantly, the function has to be differentiable on the open interval from a to b. That means we don't really have to worry about the differentiability of the function at the endpoints, but in between, our function needs to be differentiable. If these two conditions are both met, then the mean value theorem says at some point on that open interval, the derivative of our function, the instantaneous rate of change, is going to be equal to the average rate of change. All right. We talked about instantaneous rate of change and average rate of change last fall. The instantaneous rate of change is another phrase for the derivative at a particular point, and the average rate of change, we know that to be the slope of the secant line. Right? So let's put this in terms of a couple of pictures to see what's going on here. So let's take some value. We're just going to pick this value right here on this first graph. That's going to go through that value, and it's also going to go through, say, this value right here. Okay, so at -4, -3, and also 3, 3. So we're going to have a function, and we want that function to be both continuous and differentiable. So I'm going to have a nice, smooth function. Okay, a nice curvy function from one to the other. No issues with differentiability, no issues with continuity. Okay, so because our function is continuous and differentiable, the mean value theorem kicks into action. And here's what the mean value theorem says. If we look at the average rate of change, the slope of the secant line, all right, so this goes way back to when we talked about our trip to New York City. Here's the secant line, which passes through both of the endpoints of our interval. Okay, there's our secant line. That secant line has a slope. Okay. The mean value theorem says at least one time, at least once, there's going to be a spot such that the derivative is equal to this average rate of change. So the average rate of change is the slope of this blue line. We know the derivative is the slope of the tangent line. So two lines, their slopes are the same if the lines are parallel. So in other words, somewhere on this curve, we should be able to draw a tangent line which is parallel to our secant line. And sure enough, somewhere right around there, okay, if we draw this tangent line, we can see the tangent line is the parallel line to the secant line. In other words, two lines are parallel, the slopes are the same. Okay, and this has to happen. This line has to exist because the function is both continuous and differentiable. Okay, so if we split this up again, now it could happen more than once. It has to happen at least once. Let me give you a situation where it happens more than once. All right, so let's say that we look at this situation right here. Okay, that function is also continuous from A to B and differentiable. There are no corners, no cusps, no discontinuities, no vertical tangent lines. Okay, so once again, I'm going to draw my secant line in pen here, blue pen. All right, and I have to have at least one tangent line which is parallel to this blue secant line. But in fact, I've got one here, I've got another one right there, I've got a third one right here. So I've actually got three tangent lines which are parallel to the secant line. We were guaranteed at least one. There could be more. Now again, the mean value theorem doesn't tell us what this value of C is. It doesn't tell us where these tangent lines or a tangent line will occur. It just says that it has to occur. All right. So you want to be ready to find the average rate of change when you're asked about the mean value theorem. Or you also want to be ready to check on the conditions. All right, so let's bring our situation in another time. Okay, here's our points again. But this time I'm going to draw a function which is not differentiable on the open interval. Okay, I've got a corner right there. Right. So again, when I draw my secant line, right, there's my secant line, because the first condition is true, Okay, our function is continuous. But the second condition is not true because we are not differentiable at that value when x is equal to just a little less than -2. All right, now the mean value theorem no longer guarantees that we're going to have our tangent line. And sure enough, we cannot draw a tangent line which is parallel to this secant line. I can draw a tangent line here. I can draw a tangent line here. I cannot draw a tangent line at the corner. So neither of these tangent lines, nor is any tangent line going to be parallel to our blue secant line right there. And that's what they love to test as well, is the student realizing that the function needs to be differentiable on the open interval. Okay? If the function's not differentiable, this may not happen. It could happen, but it may not happen. All right? If the function is continuous and differentiable, then this situation with the parallel secant and tangent lines, this will happen. That is your mean value theorem. So you want to know both the conditions and the conclusion, okay? And you also want to be ready for this where they don't actually state the phrase mean value theorem. As we'll see as we advance through the course, sometimes the question writers will say, does the mean value theorem guarantee blah, 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 okay? And sometimes they'll say, is it guaranteed that this happens? In other words, they're referencing the mean value theorem, but they're not actually stating it.